Okay, so now we're going to do our biostats review. Any questions before we begin?
You're posting this later.
I'll post this later, yeah. Okay, so what is meant by standard error of the mean? These are kind of representative of test questions you might be seeing on the exam. This might not be the exact questions, but they are similar in spirit. You think so? Okay, well, I already wrote the test, so I'm sorry. Can't do that. Okay, so what is meant by standard error of the mean? So is it an estimate of the standard deviation of a group of samples around the population mean? You think so? Okay. Is it a measure of the frequency of an occurrence over some time interval? So B you can pretty much rule out, right? B doesn't sound right. C, it represents a relationship between sensitivity and specificity? No. Certainly not. Sensitivity and sensitivity and specificity, no, certainly wouldn't that either. It's a mathematical equation to convert non-symmetrical data into normal distribution. Yeah, it's that log normal distribution we were talking about. So the answer would be A in this case, right? So standard error of the mean is trying to determine how close your mean that you got in your sample kind of truly approximates the mean of the population, right? And what do we say affects the standard error of the mean? If I increase this, I will sample size, absolutely. So you increase sample size, you can decrease your standard error of the mean because you're closer to that true population you're pulling from. Good. Okay, so suppose a clinically accepted value for mean fasting glucose in females aged 20 to 29 is 100 milligrams per deciliter, and the standard deviation is 10 milligrams per deciliter. The fasting glucose for a 25-year-old female came back at 130 milligrams per deciliter. How many standard deviations above the mean is the subject's fasting glucose? Think three?
Hopefully.
Think three? Absolutely, so it would be 3, right? Because she's 100. One standard deviation would be up, 110, 120, 130. Okay. Yep, that's about the math you got to do. So what percentage of patients do you think would have a value of 130 or higher than that? I think 95?
They would have higher than 130?
Yeah, higher than 130.
0.01?
It's very, very small, because remember, when we have one standard deviation in either direction, what percentage of values do we accounted for? It's like 68.5 or something. We don't really care about one standard deviation. But 2 standard deviations is 95%, and then 3 standard deviations is 99 point whatever, right? So it would be very rare that you'd have someone with a fasting blood glucose greater than that, right? Assuming she was, normally distributed, random sampling from the population. So so keep those concepts in mind. Okay, so in statistical analysis, an alpha or type 1 error refers to which of the following? So the probability of rejecting the null hypothesis when it is true.
No.
Think no? So the null hypothesis is true and I've now rejected it. That's a type 1 error, right? It's type 1 error. So the null hypothesis is true, now I've now rejected it. So it's a false positive, right? Yep, so that would be type 1 error. What about the probability of failing to reject the null hypothesis when it is false? That's a type 2 error, perfect. Also, that's going to be used with beta, right? It's our level we set for making type 2 errors. It's useful in power calculations. How about the probability of keeping both the null hypothesis and the alternative hypothesis when neither is true? That's just nonsense. And then the probability of rejecting both the null hypothesis and the alternative when both are true, again, also nonsense. Good. Okay, so then we have question 4. So suppose a clinically accepted value for mean systolic blood pressure in males, age 20 to 24 is 120 millimeters of mercury. Standard deviation is 20. What proportion of readings would lie between 80 and 160? I think 95. Why? 2 standard deviations, so 95% of patients should be in that range, right? Perfect. What would, if I had, say I was looking at the 3 standard deviations, what range of blood pressures would I look at? 60 to 180, right? So again, you just do like another 20 millimeters of mercury either direction, right? So that would be, the extremes of blood pressure there. Perfect. Okay, so using the empirical rule, what percentage of observance will lie between 3 standard deviations of the mean? Already talked about that. D would be that one there. Okay. If significance level alpha is set to 0.05 and a p-value of 0.1 is obtained as a result of the study, what does that indicate? The results of the study are statistically significant? No. Okay, that's true. The results of the study are not statistically significant. That you could take that away from it, right? Because again, it did not fail to achieve your specified alpha level 0.05, so you can't reject the null hypothesis. You're unable to determine whether results are statistically significant. You can, because you have a p-value, right? That tells you right there. The results of the study are more reliable than expected. Not necessarily, right? We can't really take that information away from just having one non-statistically significant test. Now, just because I got this p-value of 0.1, does that mean I've made a type 2 error? Not necessarily. It's possible I could have made a type 2 error because I failed to reject the null hypothesis. But again, when you're looking at type 2 rates, typically you set that at a level of 20, or 0.2. So in basically 1 in 5 cases, could be a type 2 error. But we don't know that, so we just go with the results. We do not reject the null hypothesis because you'd rather make a type 1 or type 2 error. Type 2 error, right? Rather not find a result, find a difference, than find one that's not really there. Okay. The width of a confidence interval is influenced by which of the following? The standard error of the mean. No, right? Because that's really just talking about how close our mean is to the population mean, so that's not going to affect it. The p-value. Think so?
Not anymore.
No, so not necessarily. So typically, you're not going to see the p-value really affect the size of the confidence interval, right? So you're not going to see any association there. How about the sample size?
Yes.
Absolutely. So the bigger the sample size, smaller confidence intervals, right? Because there's less variability in the data. I know it's going to be closer to a true mean, so that's going to be one of the biggest changes there. And F ratio, that's just something we talk about when we're using things like degrees of freedom and t-tests and whatnot, so don't worry about that.
So they're inversely proportional, you think?
Yeah, so as sample size goes up, confidence intervals are going to shrink. Perfect. Okay, so let's say you're reviewing a survival analysis study in a medical journal, and you astutely note that a study has an N of 200, so 200 people. All enrollment happened in year 1, and the study ran for 10 years. So at year 2, we had 177 people left. At year 2.9, we had 165. At year 5.8, we had 100 subjects remaining, and at year 10, 75 remain. The median survival time for this study would be which?
Do you know that they're dead, or they just lost a follow-up?
They're dead. Did it myself. I made sure. So what do you guys think? What is the median survival time? Think C? Why? Yeah, so when 50% of the people are gone, right? They're out of the analysis now. So again, 5.8 would be your median survival time. Why do we use median survival time versus average survival time? Exactly. Everyone would have to be dead in order to actually do a comparison of mean survival time, which could be possible if you went for a long enough study period, but usually that's kind of impractical. You want to leave some people alive, otherwise they won't come back for your next study. So in this case, 5.8 years would be correct. All right, which of the following variables is spaced with equal intervals or distances and the 0 point is not considered meaningful? So is it a ordinal variable?
No.
No, right? Because what would be an ordinal variable?
Ranking.
Yeah, it's just a ranking of things. There's no implied relationship between the distances between different ranks, right? Is it a continuous variable? This one's kind of a trick one. This one I did not intend to do that, but it is what it is. So it is a continuous variable, but what type of continuous variable is it? Because again, interval and ratio are kind of a subset of continuous variables. I think it's a ratio. The 0 point is not considered meaningful. It's an interval, right? So that'd be a case like if you're looking at like temperature in Celsius, right? Where just because you have 0 degrees centigrade, it doesn't mean there's no temperature, right? 0 point doesn't really matter. So and that has implications when you're looking at how you can compare different values together. So you can't do ratios of temperatures in centigrade because the fact that the 0 point doesn't matter. So if I had a negative versus a positive, like It just doesn't work. Now you can look at average, mean, and change of temperature. That could be a ratio variable, but if the 0 point doesn't matter, it's going to be an interval ratio or interval variable. Okay. Which statistical test is best used to summarize a case control study? Relative risk. When would I use a chi-square goodness of fit test? So I would use chi-square if I'm looking at something, I'm looking at the occurrence of an event, or I'm looking at a frequency, and I want to see whether the actual frequency is different than what would be expected to happen by random chance, right? So think back to that fireman example where we're looking at there's a higher number of deaths that occurred when they were actually fighting fires, even though that was a very small proportion of their time versus doing other activities, right? So that would be a good example of a chi-square test. I can look at the actual number of deaths that occurred versus what I would expect and see if there's a statistic difference there, right? So that wouldn't be it. How about survival analysis? Now, survival analysis usually are going to be looking forward. You're going to be looking at as they die off or the event occurs. Okay, so that leaves us with odds ratio and relative risk. Which one do you think it is? The odds ratio? So it's like 50-50 in here, right? So this is actually going to be odds ratio. The reason for that is because odds ratio is using prevalence in order to figure that, right? Because you're looking at your odds of something occurring versus not occurring. And when you're looking retrospectively in these case control studies, you're using odds ratios because you can use that snapshot of prevalence at that time period, right? I can say these people had the disease, these people didn't. Versus if I'm using a prospective study, I'm using incidence of new events occurring. For that, I'm going to be using relative risk. So please keep that rule of thumb in mind. All right, researcher is seeking a statistical test that can determine whether the means of several groups are all equal. Which of the following would be the best test that this researcher would select? You want to do ANOVA? Why? Several groups, right? If it was two groups, yeah, I could potentially use like a t-test, right? So a two-sample t-test, when would I use that? It's actually made up. That doesn't mean anything. One sample t-test would be if you're comparing a sample mean versus the population, right? If there were, say, it was only two groups and they were unpaired, what would I use?
Unpaired t-test.
Yeah, an unpaired t-test. And then for this one, would I use a one-way or a repeated measures ANOVA? A one-way? That's right. Do you know why you're right? So if the groups are unpaired, you would use a one-way ANOVA. If the groups are paired, use a repeated measures ANOVA. Okay, let's keep that in mind. How about a Mann-Whitney U-test? This is good. So you use it with what type of data? Non-parametric. Right, non-parametric data. Okay, so it's my non-parametric test. So I'm not, because I'm worried about outliers and I'm worried about the data not being normally distributed, I'm worried about, I'm more going to use medians and use ranking, right? So good, so I'm going to be ranking things. What type of groups would I be comparing to use a Mann-Whitney U-test? So think about this one as an unpaired t-test for non-parametric data, right? So the Mann-Whitney U is going to be for unpaired comparisons of means with non-parametric data, right? And then the Wilcoxon is typically used for paired data for non-parametric. Okay, so be able to identify those, based on the type of study you're doing, what type of test you should be using, right? Based on the population you're looking at. And I'll be very explicit about saying this is non-normally distributed data, or this is a Gaussian distribution. I'll be explicit about that. Okay. So a laboratory test that correctly identifies patients with a disease state is said to be which of the following? So it correctly identifies patients. Yeah, so it's sensitive, right? So it'd be very sensitive in picking up patients who actually have the disease state to say, yes, this is positive, right? If I said it correctly rules out patients for having a disease state, I would say it's specific, right? Accuracy we're going to talk about probably more in the epidemiology section, so don't worry about that. Okay. Looking at this one, I'm actually not going to make you do a calculation like this, but this is a good example. So how would I calculate the likelihood ratio for a test with a sensitivity of 90% and a specificity of 55%? Can anyone even tell me how to calculate that?
90 over 1 minus 55.
Perfect. Yeah, 90 minus 1 over 90 over 1 minus 55. And what does that come out to be roughly? 2. Yep. So the likelihood ratio here would be 2. Okay.
90 divided by 45.
It was real quick too. I agree. Okay. So I won't make you guys do a calculation like that, but just be aware of what this means. And again, if I had a likelihood ratio, do I want a larger number or smaller number to show that something is more likely to be predictive of say a disease state? Yeah, you want a larger number, right? To say like, okay, if you have a right lower quadrant pain, you probably have appendicitis, right?
Yep.
Thank you. We're so glad you're back in full health. Taking the test on Friday, that was amazing. Very proud of you. Yep. Okay. I'll give you an answer on the test. C. Yep. Perfect. You already knew. See? Is that good? Okay.
You give an answer, cut mine out too.
Yes. All right. So which of the following is a nonparametric test used to evaluate nonpaired data? I just said it. Wilcoxon? Man Whitney. Whitney was a man, maybe. I don't know. Okay, good. So that's correct. Man Whitney U test would be the correct one there. Okay. Which of the following tests is used to assess the observed versus expected findings of a study? Yeah, chi-squared goodness of fit test would be the correct answer there, right? Because you're looking at expected versus actual frequencies and comparing them. Okay. Which of the following statistical analyses would find the line that best predicts y from x? I think A. So it's definitely not C. We already talked about that one, right? Because that's just talking about frequency and whatnot. Why is it not D? Right, because that's telling us whether or not the data that we have appears to be from a normally distributed data set. So that would not be correct. So then you have linear versus nonlinear regression. Again, we said in this case it's just a line. We're not saying the curve the best fits it, so it would be A, linear regression. Perfect. Remember that the nonlinear regression, even though that it better fits those data points very frequently, it's a lot more difficult to compute, and oftentimes it's kind of just fitting the data too well. So in a lot of cases, you kind of lose a lot of that variance that occurs from that. So again, very frequently you see more linear regressions being done than nonlinear. I might have forgotten to renumber my slides. That's probably what I did. Yeah. There's a hidden slide, 16. Nope. Yeah, I probably just accidentally skipped it. Okay, which is the most sophisticated method of data measurement? Sophisticated meaning I can do the most stuff with it. So we can rule out internal because that doesn't make sense. We didn't even talk about internal, right? If it's an interval, would that be right?
It wouldn't be right, but
It'd be close, but it wouldn't be correct. So which is going to be the most sophisticated?
nominal.
So again, nominal, what can I do with nominal?
We can do all kinds of number calculations with
Well, I can say like, okay, so I have, green eyes, blue eyes. Can I do a ratio between those two? No, I can't divide green eyes by blue eyes. It doesn't make sense, right? I can do frequency tables, but I can't do much else than that. How about ordinal data? I can do medians, I can do quartiles and things like that, but I really can't do any true ratios because, again, there's no set relationship between one value to the next. So in this case, it would be ratio variable, right? Because that's a continuous variable. The difference between 1 to 2 and 2 to 3 is going to be the same no matter where I'm at in the scale. 0 makes a difference, so I can start to do ratios between those values. So again, that's going to be an important one there. Let's do one more. Which of the following study designs is generally accepted as the most reliable evidence that a treatment is effective? Yeah, randomized controlled trials are always going to have the greatest strength of showing that there's actual cause and effect going on here, right? So if I did, say, a case series, what type of study would that be, do you think?
observation.
Not necessarily observational, it's more of the descriptive kind, where you're just looking at a number of different cases that occur, and again, you're not drawing any conclusions from that, you're really just describing them, right? Versus if I did case control, that's going to be what type of study?
Experimental.
It's experimental, but it's one of those observational ones, right? I'm sorry, it's observational. It's more of an exploratory trial where you're looking to draw a conclusion by looking at retrospective data. But again, cohorts are very similar to that, and then you have your randomized controlled trials, which are prospective, and you can actually draw a true kind of cause and effect analysis from that. So I'm going to record the rest of this, and then I will post it up online. If you have any questions, let me know. Okay, we're going to go ahead and finish up with just a few review questions to help you guys get ready for the exam. So to pick up where we left off, here's question 20. And so the question is, which of the following tests make no assumption about the population distribution? So based on that, we know that one, we can rule out D, because normality tests are typically used to tell us whether or not the sample that we're looking at is normally distributed. So in this case, this would not be, this is testing to see what what kind of assumptions you can make, and it really wouldn't count in this case. Chi-square test we've talked about previously. We know this is just helping us to look at frequencies of events and seeing whether or not it is distributing from what the expected occurrence rate should be. And so then you're down to your parametric and non-parametric tests. And as we said, this is a very key thing to understand about medical statistics, and that with your parametric test, this is assuming that you have a normally distributed data set, and then your non-parametric tests make no assumption about this. So because it makes no assumption about the distribution of the data, you can start to use your non-parametric tests, which are going to be more robust and thus are more difficult to make a type 1 error. So it's harder to achieve significance with those type of tests because, again, you're not making any assumptions, and so you can basically say that if you do actually find a difference with the data you're looking at, that there truly is a difference there. Okay, so this is going to be an example of a little bit more kind of in-depth or critical thinking based kind of application of our biostats in interpreting the literature. So for instance here, we're going to say that we're reading an article in which the investigators wanted to compare treatment of a new diabetic medication with placebo on fasting blood sugar. The researchers randomized 40 patients to either receive placebo or drug X, and then the researchers used a paired t-test and found that patients in the experimental group had a mean difference in fasting blood glucose of 10 milligrams per deciliter, meaning that when they received drug X, they had a reduction in fasting blood sugar of 10 milligrams per deciliter. You can see the confidence interval here ranging from -21 all the way up to +7. And so which of the following conclusions would be correct? A, these results are clinically and statistically significant. So based on this, you can already rule this one out. Because we are subtracting means from one another, you can see the difference between drug X and placebo. Because we're subtracting that, we're going to use 0, or anything that our confidence interval crosses 0, we're going to use that to determine non-significance. So in this case, when you did the subtract one mean from the other, you end up getting a mean difference of 10 milligrams per deciliter with this confidence interval that range from a negative number to a positive number. So we know that's going to encompass 0, and so based on that, we can already rule out the clinical or the statistical significance of this finding. Now, it could be clinically significant, may not be. That's going to be a little bit more subjective, but in this case, even though we don't have a p-value, we can already rule out A and say that this is not statistically significant. Moving on, the researchers may be making a type 1 error. So in this case, we cannot say this because of the fact that the results were not statistically significant, and so that would automatically rule out a type 1 error. Now, you could say potentially you're making a type 2 error, but that's going to come more into play when we're talking about one of the other answers. So next, we're going to say that the researchers are using the paired t-test correctly. This one you can say is incorrect because when you're looking at the patients, they're basically randomized to either one group or the other. So because these are independent and unpaired groups, using a paired t-test would be incorrect and so would not be appropriate in this case. So that leaves us with D. The researchers may not have had enough power to reject the null hypothesis, and this would be true. So this would be an example of a type 2 error where there is a true difference, but you fail to reject the null hypothesis. So essentially you're getting a false negative in this case. So, if you had redone the study and say instead of using 40 patients, you use 400 patients, it's very possible that that reduction in blood glucose might have actually shown a statistically significant reduction versus here where the results are not statistically significant. So in this case, the answer would be D. So here we're going to be looking at the same article, the same situation, and now we're going to try to see what other conclusions we can draw from this data set. So A would be the fasting blood sugar is a confounding variable. This would be incorrect because this is actually our outcome variable. This is the thing that we want to see what is changing based on our intervention, which is be either giving patients the drug or giving them placebo. So because of that, it's not really a confounder. Now, for instance, if you were looking at, say, outcomes, say you're looking at changes in creatinine clearance as a surrogate for progression of diabetic nephropathy, you could potentially say that fasting blood sugar could be a confounding variable, because if one group had a much higher resting blood sugar than the other to begin with, then that could be potentially causing accelerated damage to the kidneys and could be confounding your results. But in this case, since it's the outcome variable, we don't want to say that this is a confounding variable. Next, we're going to see whether the patients receive drug or not is the dependent variable. We're going to say that's false because essentially by talking about A, we already said that fasting blood sugar is going to be our outcome variable. In this case, it's going to be our dependent variable. So whether the patient got the drugs or not, that's what we're determining. That's what the researchers have decided. So because of that, that is going to be the independent variable. And then whatever outcome changes based on our independent variable, that will be the dependent variable. So in this case, fasting blood sugar would actually be your dependent variable. So B is going to be incorrect as well. Next, we're going to look skip C for a second and go ahead and go down to D. And so we're going to say that fasting blood sugar is an ordinal variable. And of course, you know that this is incorrect because basically it's a continuous variable. Blood sugar, has a continuous number that can run from. We know that it is has a very set difference between one value to the next. So for instance, the difference between 10 milligrams per deciliter and 20 milligrams per deciliter is the exact same difference as you would see between 110 and 120 milligrams per deciliter. So because of that, because there is a set value or a set basically distance between each integer there on the scale, it's not going to be ordinal, right? So in this case, you could rule out D as well. And then looking at C being our final choice, so adding a third group receiving a different dose of drug X would require use of ANOVA. And this is true because, again, when you were looking for the difference in means between three groups or more, you basically want to use an ANOVA at that point to avoid falling into multiple comparisons issues. So C would be the correct answer here. Okay, so you're going to perform now a case control study in which you're looking at patients who contracted measles versus control cases that did not, and then you're determining whether or not they were vaccinated. Which of the following statements would be true? This is an example of a prospective study. This one you can rule out because, again, we're doing a case control study and we're looking at patients who have already had the outcome. So we're looking for patients who either had measles or the control cases which didn't. So because we're looking backwards, this would be a retrospective study. We're going to skip B for a second and go to C. This is an example of a randomized control trial. We already said this is a case control study, and in order for us to have a randomized control trial of this type, we would essentially have to take patients and randomize them to either, say, receive the vaccine or not receive the vaccine, and then carry out data going forward and see which of those patients ended up contracting the disease or not. So because those are very difficult studies to do, and because of the ethical implications of that, very rarely do you find studies like this being done in a randomized control kind of sense, at least in a prospective sense. And then looking at this, relative risk would be the best way to report efficacy of the vaccine at preventing measles. We know this to be incorrect because, again, we are looking retrospectively. We are looking at the prevalence of the disease, and so risk would not be ideal to look at that. You'd want to actually use the odds ratios at that point. So we've kind of talked about that previously. And then looking at this, vaccination status is a nominal variable. That would be correct because basically you can either be vaccinated or not, right? So this is also considered to be a dichotomous variable because there's only two outcomes for it. But this would also be falling into the category of a nominal as well because, again, it's just a name you're applying to a group, vaccinated or not. Similarly, whether they got measles or not is also going to be a nominal variable. So contracted measles, didn't contract measles. Both are going to be nominal variables. So for your last question, you're performing a study in which you're randomizing 3 independent groups of patients, N is 120, to receive either 30, 60, or 120 milligrams of oral pseudoephedrine, otherwise known as Sudafed, and measuring the mean changes in blood pressure. Which of the following is true? I'm going to skip ages for the time being, but go down to B. saying that the null hypothesis would be that a 120 milligram dose of pseudoephedrine would increase blood pressure the most. You can automatically rule this out because in this situation the null hypothesis would be that despite whether you receive 30, 60, or 120 milligrams of oral pseudoephedrine, you should have the same change in blood pressure. There really should be no difference between the three groups here. So you can already rule out B as being false. Next, we'll look at C, where the method of measuring blood pressure does not need to be included in your results. This would actually be false because you should really be stressing the importance of being thorough and being as transparent as possible in study design, and researchers should be doing this as much as possible. Basically what I mean here is that by using, say, you were measuring blood pressure by manual auscultation for some patients, and then, say on a different day, you're going to go ahead and use an automatic machine to do so, and it'll just vary based on what you feel like for that day. So because of the fact that there could be inaccuracies in how the measurements are being done, either if it's done manually or say the machine is miscalibrated, whatever happens to be, it's important that you're going to say that, listen, we're going to be measuring blood pressure the same way every single time in order to make sure the results are consistent. So in this case, C would be false. Then going down to D, a repeated measures ANOVA is needed to determine if you can reject the null hypothesis. This one would be false. Even though we have three groups here that are being compared, repeated measures ANOVA is going to be used when you have paired groups. And in this case, we have three independent groups. Now, say for instance you had patients who were given 30 milligrams on, say, day 1. You give them, say, a 2-day washout period for the drug to be metabolized and leave the system. Then you give that same patient 60 milligrams, the same washout period, and then did 120 milligrams. So if you were using the same patients receiving different doses, those would be a paired, an example of paired groups, and repeated measures ANOVA could be used to determine if there's a difference between those means. In this case, they're all independent groups, so you would use just a one-way ANOVA in order to reject the null hypothesis or not. So that brings you back to A, where we would say performing multiple unpaired t-tests would lead to an increased chance of a type 1 error. And so this is absolutely true. Because we are comparing the means of three groups, you want to go ahead and not use unpaired t-tests to go ahead and check for differences between each of those groups, comparing 30 to 60, 30 to 120, 60 to 120. That increases your chance for type 1 error. So in this case, what you should do is use a one-way ANOVA to check to see if there's a difference between any of the means, and then if that is positive, if you can reject the null hypothesis, then at that point you'd use some corrections and using multiple comparisons tests to look to see which pairing is truly going to be significant. So in this case, A would be the correct answer. So I hope that kind of allays some of your fears. I think the test is going to be this review is very representative of what the test is going to include. But if you have any questions, I will try to be as available as I can the next upcoming days. And feel free to email me, stop by my office, whatever you like. We can talk it out from there. Thanks so much.